Hi everyone, welcome to today's lesson. We're going to be looking at functions of several variables. And to start off, we're going to look at the definition for a function of two variables. This says that a function of two variables is a rule that assigns to each ordered pair of real numbers x, y in a set D a unique real number denoted by f of x, y. The set of values that f takes on, that is, all of the values within that range, or f of x, y, such that the ordered pair x, y is in the domain. That is the function that we're looking at when we're talking about the range of that function. Now, we've seen some of these functions before, and we've seen some of them in terms of x, y's, and z's that we were introduced with in those types of equations back in chapter 12 when we were looking at surfaces. And now we want to formalize a little bit more. We want to formalize that definition a little bit more in order for us to start working with these functions of several variables. Very similar to algebra, when we were extracting equations and we were graphing equations of lines, equations of parabolas, hyperbolas, all of those equations that we were graphing, only a few of those equations actually made the cut to become functions. They had to pass a certain definition, right? And the definition was very similar to this definition that we're given for the functions of two variables. And what we want to do is we want to keep on exploring this whole topic of functions of two variables, or in this case, several variables. And we're going to do this by analyzing what is the domain, what is the range, and what are some of the projections of this surface onto the respective domain. But in order to answer those questions, we again have to dive into the material in order to get those questions answered, or so that we can start viewing some of those topics. So on your screen here, I have two examples. It says that for each of the following functions, we want to find and sketch the domain. And so finding the domain for these types of functions, these functions of several variables, we're still going to go through the exact same process that we did before this class. In order to find a domain of a function, we then have to identify what values could make my function undefined. If we find those, we'll remove them from our domain. And we also want to find what values will my function not be defined for on the real numbers. In other words, what inputs would get us imaginary numbers, if applicable, and then we would remove those values from our domain. And we can see on part A, for that rational fraction that we're given, or that rational equation that we're given, what we want to do here is we want to look at the numerator, and knowing that my numerator is I have a radical on that numerator, and extracting that inside of that square root, we cannot have negative values. What we're going to do is we're going to take that radicand and we're going to set it greater than or equal to 0. This will then give an equation or an inequality as y is greater than or equal to negative x minus 1. And we're going to kind of keep that in our back pocket just really quickly, because this is one of those restrictions that we must apply. The other restriction is that the denominator cannot be 0. So my denominator cannot be 0, and in that sense, whenever x is equal to negative 1, or sorry, in this case 1, we're going to make sure that we omit that. Now, the nice part about this is that x is equal to 1 is just a vertical line. So we're going to kind of keep that in mind here. Okay, so what I'm doing right now is I'm putting tick marks on my grid. Perfect. Okay, and I'm going to identify 1 and -1 on my axes here. And so again, x is equal to 1 or not equal to 1. This is going to be a vertical line. And this vertical line, since it's not going to be a part of my domain, what I'm going to do is I'm going to exclude this value. In other words, I'm drawing this dashed line because this dashed line will not be a part of my domain. I'm also going to identify this y is greater than or equal to -x minus 1. Well, -1, that's its y-intercept, and its slope is -1, so it goes down 1 over 1, or we could go up 1, back 1. So up 1, back 1, there we are. And all we're going to do is we're going to create another line here, and we're going to make this dashed because, or sorry, not dashed, we're going to make this solid because it's going to have to be everything greater than or equal to this line. If this line here was, I don't know, let's say this line was not equal to. If it was only y greater than -x minus 1, then this would be a dashed line. However, in this particular case, because we do have an equality here, we must do this as a solid line. And now all we want to do is figure out, well, where is the domain? Is it above the orange line or is it below? And the inequality actually tells us where this should be. Okay, so this tells me that y is going to be greater than that line, so all of the values are going to have to be greater, meaning above it. Or what you can do is you can pick an ordered pair either above the line y is equal to -x minus 1, or you can pick an ordered pair that is below that line, and you can test them into your inequality. Whichever inequality works, that's the inequality that you go with. And so my domain here is going to be this portion above. So this is going to be all of the domain that we are working with. Now again, we're not going to include anything on the dashed lines. So anything on the dashed line we're not including. It just kind of, my marker just kind of got all over that. But essentially this is a domain of that function that we're asked to observe. And so we found the domain and now we sketched it. Let's go ahead and let's verbalize the domain just a little bit more, that way we can fully identify this. So I'm going to say the domain of f of x, y is a domain D, where this is going to include every x and y coordinate where y is greater than or equal to -x minus 1 and x is not equal to 1. As such, that is the domain of the function. And again, this domain is in set builder notation, and we want to keep using set builder notation as we proceed with a lot of our domain identifications. Let's look at the second one, part B. Looking at part B, again, what I see here is that on my numerator I have a natural log, and we know that the arguments of natural log must always be positive. So in that sense, we're going to take the argument of the natural log and we're going to set it greater than 0. This is going to show us that we're going to get that 2 is greater than x, or we can say that x is less than 2. We also get a denominator where the denominator cannot be 0. So I'm going to take my denominator, and I'm going to make sure that this is not 0. In that sense, we now get that the circle centered at 0, 0 with radius 1 will not be included. So let's go ahead, and I'm actually going to move this a little bit. There we are. Let's move this over here. There we go. Perfect. All right, so let's go with that. Let's put some tick marks on here. Oops. Okay, perfect. Cheese and crackers. There we go. Okay, perfect. So what I want to do now is I want to find x is equal to 2. And so when I'm looking at x is equal to 2, or in this case x is less than 2, what that's telling me is that I'm going to have a vertical line at 2. And this vertical line is going to be dashed. There we are. And so again, this line is x is equal to 2. Now, less than 2 is going to come into play when we want to identify what domain we're observing. So far we know that the x value cannot be 2. Okay, great. Now we're going to look at my circle. Circle centered at 0, 0 with radius 1. And again, we're going to make sure that we're not equal to this circle. Which means that circle has a dashed line around it. The values that we're looking for are all the values that are less than 2, or x is less than 2. That means that all of these values to the left will work, so long as they are not on the circle that we've identified. And that's why we're going to leave that dashed circle there. So again, you exclude these values from the circle, which will be perfectly fine. And then after that, you exclude the boundary points on that vertical line, and you have your domain. So let's make sure we outline this. This is going to be the domain for g of xy. And this domain is going to be domain D. It's going to contain all of the ordered pairs xy such that x is less than 2 and x squared plus y squared is not equal to 1. There we are. That is the domain. So again, we want to make sure that we extract these values for the domain, and we have to make sure that we keep on applying these techniques that we've learned in previous courses. Now, at the bottom of your screen here, we're going to formalize this function a little bit more. And we're going to say that if f is a function of two variables, like we saw in part A and part B, with the domain D, then the graph of f is the set of all points x, y, and z in R space 3 such that z is equal to f of xy and xy is in the domain D. So what that means now is that when we're classifying these functions as we did in part A as f of xy, we could technically assign this a value of z. And we can say z is equal to this function. Therefore, the output will be some z value. And the collection of all the three components, the x, the y, and the z, the collection of all of those points will then generate a graph in R space 3. That's what this final definition was saying. So what we want to do now in this example is we want to find the domain and the range for this function h of y. So this example gives us a function h of xy, which is the square root of the quantity of x squared minus 1 plus y squared. And again, we want to find the domain and the range for this function. Alright, so let's work on identifying the domain. And again, what we want to look at for the domain here is going to be taking the radicand and setting the radicand to be greater than or equal to 0. This will get us x squared plus y squared is greater than or equal to 1. And what this says then for my domain of h of xy, the only restriction that we have here is that our ordered pairs have to satisfy the circle or the equation of that circle or this inequality for that radius to be greater than or equal to 1. So that's a restriction that we get for this domain. Any circle that has a smaller radius than 1 will not work, will not suffice for this particular example. So let's go through now and let's now start looking at the range. In other words, what are the possible outputs? Okay, so what I want you to do is I want you to think about what's the smallest x and what's the smallest y value that we can think of that can possibly satisfy this particular equation. Well, they both cannot be 0, x and x cannot be 0, and that kind of satisfies this particular domain that we were initially looking at, that the ordered pairs have to be greater than, or sorry, the sum of the squares of the ordered pair components must be greater than or equal to 1. So x and y can neither be 0 and 0, 0 at the same time. However, let's look at when x is 0 and y is 1. Well, that satisfies it because then we get the square root of 0, which is 0. And I do believe that that's going to be the smallest value that we can take on for h of x, y. So h of x, y, the smallest it could be for the range is 0. Now remember, the range for this function h of x, y, the range is just an interval because the interval here is going to give us the values for the z values. So the interval is only talking about one specific axis, and that's the z-axis. So in this particular case, the smallest z value that we could have is 0. Okay, that's nice. Well, what's the largest then? Well, x and y, according to my domain restriction, they're just going to be unbounded so long as the radius, when we identify for that circle, is going to be greater than 1. So that means your x's and y's are unbounded, therefore you can take any larger value for that radicand, and the square root of that will just basically send you off to infinity. And so here now we've identified the range and the domain for this function. Great. Now let's look at what are level curves. And I have a definition down below on your screen here that says that the level curves of a function of two variables are the curves with equations f of x, y is equal to k, where k is a constant, but the constant must be in the range of your function f. And I also have on here that a collection of level curves is called a contour map. And what we want to do here is we now want to create a contour map for this function that we were initially working with, and then we want to sketch the function. So these level curves are kind of like these projections that we were looking at when we were working in section 12.6 with surfaces of these functions, or these surfaces that we were going to be working with. And when we were looking at the projections, we were basically looking at the projections onto the x and y coordinate system, or onto the x and z coordinate system, or onto the y and z coordinate system. And in this particular section, we're going to limit all of those projections to just one projection. And that one projection is going to be using the domain. So when we look at our function is now broken off into saying that we have an h component, and that's going to be the overall function, and that's going to be that z component that we look at. So the overall evaluation of this function produces z values. In other words, they produce your range. The variables are x and y. Therefore, the domain will be in x and y components. So when I want to build a contour map, we now have to choose values within that domain so that we can start analyzing what are these level curves looking at. So in order to find those level curves, we then have to find constants that are in the range of this function. And that's where we have to be careful, because sometimes we're going to see that we might want to choose specific outputs. However, those outputs have to be in the domain. And if we're not careful enough, we might choose incorrect ones. So I'm going to say here, choose values for h of x, y is equal to k. So in choosing those values, we can go and we can choose one of them. Let's say that, let's see, I'll use this color here. So let's say that z is equal to 0. Well, if z is equal to 0, then what's going to happen here, or sorry, I put z, I meant k. K or z, it's going to be the same process. So if k or z is equal to 0, then what we get here is 0 is equal to x squared minus 1 plus y squared. Squaring both sides, still get 0 is equal to x squared minus 1 plus y squared, which means we get x squared plus y squared is equal to 1. Alright, so that's one of my values. Well, let's check what happens when k is equal to 1. Well, when k is equal to 1, we get 1 is equal to the square root of x squared minus 1 plus y squared. Take the square of both sides, then we still get 1 is equal to x squared minus 1 plus y squared, which means this is going to be x squared plus y squared is equal to 2. So again, we have another circle centered at 0, 0, but the radius is now 2. And again, notice I'm picking all the values, all the k values that are in a domain, in a range for the function h of x, y. Now, you can get creative with these k values, and you can pick fractions, you can pick decimals, you can pick irrational numbers. As long as you're getting real numbers as your output, that's all that you really want to see. Now, I typically like to do this using specific integer values. So here we would get 2 is equal to the square root of x squared minus 1 plus y squared. Squaring both sides, we get 4 is equal to x squared minus 1 plus y squared, which means x squared plus y squared is going to be equal to 5. All right, and let's do one more. One more just for the fun of it. Let's do k is equal to 3. So if k is equal to 3, we get 3 is equal to the square root of x squared minus 1 plus y squared. Then we get 9 is equal to x squared minus 1 plus y squared. And then finally we get that 10 is equal to x squared plus y squared. And so in order to create this contour map, we just need this or these level curves to be graphed. And that's what we want to work on here, is we want to work on graphing those level curves. And let's see, do I still have it? Yes, I do. Perfect. So I have this coordinate system that I've already created, and again, it's in the domain. So let's put this right smack in the middle here. Perfect. Okay, so I'm going to insert some tick marks here. All right, perfect. So what I'm going to do now is I'm going to start labeling. All right, so let's go with kind of a big labels here. So we're going to go with 1, 2, and 3. -1, -2, -1, -2, and -3. We go -3. We go 1, 2, and 3. Perfect. Okay, so what I want to do now is I want to start graphing these. So the first level curve is at k is equal to 0, and this is a circle. And what I'm going to do here is I'm going to say that this is k is equal to 0. Now my next curve is going to have a radius of root 2. And that radius of root 2 is going to have an approximation for its radius as 1.4. So when we go to 1.4, so we're not going to go quite above that. So we're going to go 1.4, somewhere around here, right below 1.5. And we're going to generate that curve. There we are. And this is going to have an equation of k is equal to 1. Next curve. Well, now we got to go with the square root of 5. So we're going to go with the square root of 5, and that approximation is going to be approximately 2.2. So we go to 2.2, so going to 2 and then 0.2. So right above 2, we get that 0.2. And we're going to graph this x squared function. X squared, y squared. There we are. And again, this one was k is equal to 2. And finally, we go with k is equal to 3, and we're going to get the square root of 10 as a radius, which means we're going to approximate that to about 3.2. So about 3.2, again, we're going to go right above that value for 3. There we are, and this is k is equal to 3. So as we can see here, as we start getting closer to k is equal to 0, these level curves start bunching up together very quickly. But as we move further and further away from k is equal to 0, and remember, k's are your z values. So as long as we're moving away from k is equal to 0 or z is equal to 0, as long as we're moving in the upward direction, these curves are getting larger and larger and larger, which means they're going to be expanding at a faster rate. So what we then want to see now is, what does this look like when we're using R space 3? Okay, so let's get that going then. And again, just analyzing those level curves. That's all we want to do, is analyze those level curves and then see what we get from that. So here we go. We have our z, we have our x, and we have our y. And again, as we start looking at these level curves, then we know one of the level curves is going to be 0, 0, or sorry, the level curve is going to be at k is equal to 0, is going to be down here on the x and y axes because it's 0, 0. So I'm just going to identify that we have a curve of 1. And there's that circle. Now, knowing what's going to happen here, I'm just going to make that circle dashed. There we are. Because the next circle is going to be k is equal to 1, and that one's slightly bigger. Looks like this. The next one's slightly bigger as well. And the next one's slightly bigger. So these are the level curves that we're looking at, but what is a surface of? Well, that surface kind of looks like this funnel that we have here. And so there's our surface. It kind of looks like this, again, funnel that we're looking at. And again, this is just to get that visualization of using that domain, using the range, and then using a contour map to start visualizing what these surfaces are looking as in RSpace 3. And more specifically, not just surfaces, but we're also going to be looking for these for these functions as to what they look like in RSpace 3. So I hope that you all enjoyed this lesson, and please stick around for the next one where we will be talking about limits in RSpace 3. Till then, have a great day.